Yes. So, so last time we talked about the case when it's first order homogeneous system, and if the lambda has multiplicity k, we said the eigenvalue lambda can either be complete or incomplete. If it's incomplete, then we call it to be defective, which further would give you a number d, which is so-called the defect, okay, of this defective eigenvalue lambda I. This quantity d, which is the defect, is basically how many times the eigenvalue showed up, which is k, subtract how many regular or normal eigenvectors it has. In general, our idea is if the multiplicity of the eigenvalue lambda should be 3, then we should have 3 eigenvectors corresponding to the eigenvalue. Okay. The number of eigenvectors should match the number of eigenvalues. So if you have only 1 or 2 regular ones, then we are insured of some linearly independent eigenvectors. So that's how you calculate the d, okay, just by doing the subtraction. So last time we talked about the case when it's a simple case when an eigenvalue appeared twice. Okay, so multiplicity 2. So we went on this flow chart, we said if eigenvalue lambda has multiplicity 2, then we should have 2 eigenvectors. Basically, we can always find one at least, which is the normal one, okay, V1. And we can then check if A minus lambda I squared equals to 0 matrix or not. If the answer is yes, indeed, then we can construct V2 equals A minus lambda I V1, okay. Certain cases, the V2 may happen to be 0 vector, but we have an easy fix for that. That's what we did in our last example. Okay. So over here, yeah, and then once we figured out the eigenvectors matching the eigenvalue, then we can find the general solution by constructing x1, x2, which is the 2 linearly independent solutions. Then by using the linear combination, we can get the general solution by using those 2 solutions. All right, does that sound like what we did last time, folks?
Yes.
Okay.
Yes, so good.
Yep, so we're going to continue and talk about the more general case. Okay, so general algorithm. So we're going to talk about the algorithm. Let me see, where's my pen? All right, general algorithm. Okay, general algorithm for finding k, which is more general case. General case. Independent solutions to a linear system, okay, with defective eigenvalues. So the case here is, suppose we have a first order linear system, x prime equals ax, and we have found one eigenvalue lambda with multiplicity k, then we understand we need k linearly independent eigenvector, right? So first of all, first step, we're going to look for ordinary eigenvector, my bad. I always type eigenvalues. Eigenvectors. So first of all, let's find ordinary eigenvectors. Suppose you can find P of that. Okay. So what's going to be the defect of this eigenvalue lambda, folks?
P.
P is what you currently have, but how many you need?
Oh, you need at least multiplicity k.
Yes, we need a k, but currently we only have p, right? So the defect will be
K minus p.
Yeah, I also typed below here. So d would be the multiplicity subtract how many the ordinary eigenvectors you currently have. So it'd be k minus p. Okay. So secondly, we need to find k minus p generalized eigenvector. Okay, so these are ones we need to find. We need to find. So what we need to do is we begin with checking a minus lambda I raised to d plus 1. Okay. Check to see if this matrix would equal to 0 matrix. Let's recall the case when we have k equals to 2, which is the one that we talked about last lecture. Defect will be 1, right? Then we checked if a minus lambda I squared equals to 0 matrix. So the square over here is just a d plus 1. Make sense?
Mm-hmm.
So the case that we did last time matches the general algorithm, right? If a minus lambda I raised to d plus 1 equals to 0 matrix, if the answer is yes, okay, then we can go ahead, say if I multiply any vector v's of p plus 1, a minus lambda I d plus 1 v's of p plus 1 will still be 0 vector. Okay, so we can construct v's of p plus 2, okay, to be a minus lambda I v's of p plus 1, and then the further ones will be simply derived from the multiplication. So over here we have basically you can look for the k linearly independent eigenvectors associated with the lambda by put them into two groups. Okay, for two groups. So the first group from v1 to v sub p, these are the ordinary ones. And then the second group from v sub p plus 1 to v sub k, these are the generalized. Okay. And each one of these generalized eigenvector is related to each other. So from v sub p plus 1, you can generate v sub p plus 2. From v sub p plus 2, you can generate v sub p plus 3 until you reach the last eigenvector you need. Okay. And the way of generating is from here. Then we have said it's just going to be a multiplication of a minus lambda I times v sub p plus 1. Good so far? Does that sort of give you a sense in your mind?
Yes, I have one question though.
Sure.
It says v p plus 1 cannot be 0 vector.
No, they can never be 0 vector.
Yeah, what if we have a vector like last time, 0, 0? Do we just put anything?
Yeah, we can just put one element to be one component to be 1. Okay.
Okay.
The reason is because we already have a minus lambda I raised to d plus 1. This is a 0 matrix, right? This is already a 0 matrix. So 0 matrix times any non-zero matrix would still be 0 matrix.
Yeah, that makes sense.
Right, so v sub p plus 1 will still be an eigenvector as long as it is a non-zero vector. We'll show that in our next example. How's that?
Yeah, perfect. Thank you.
Okay. So folks, does that sort of give you a general idea of how we get to the k eigenvectors?
Yeah.
Yes.
Okay. Yeah, we'll go ahead and work on our last problem. Before that, we're going to say, what's going to be the general solutions? X of t. X of t will be based on x of i's, right? Okay, so x1 would be v1 e raised to the lambda t, correct?
Yes.
Okay. And x of 2 would be v2 plus v1t e raised to the lambda t, right? Good so far?
Yep.
Yes.
So what about x of 3? X of 3 is a little bit tricky. Okay. So we should have v3 to start with, right? And then we're gonna have, do you see the pattern sort of?
Yes.
Start with v3, and then we go v2t.
We copy.
Yeah, and then you would have v1,
T
kind
squared.
of like a t squared, right? But over here, we typically try to divide by 2. so that when you take the derivative, it's still t. Okay, this is a little bit outlier part, but the general pattern will go still your new eigenvector to be added, and then you increase the power of t. Okay, and then keep going. So once you get all of these all of these solutions, we'll just get a general solution to be C1x1 plus C2x2 plus upper new to have Cn x of n, right? It's a linear combination of those x, y's. Does that make sense, guys?
Yeah.
Yes.
We're just trying to generalize the case from multiplicity 2 to multiplicity k. Okay. Okay, so over here we should have, that's going to be the general solution. All right, so our only test today will just be using example 2 to demonstrate this algorithm that we have developed, generalized. You should have 2 pages, right? I hope that's enough space for us. So solve the system by eigenvalue method. This is x1 prime equal negative 3x1, blah, 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 blah. So let's go ahead and first of all write down our matrix A and your unknown vector x. Solution. First of all, our unknown vector x would contain 3 parts, so x1, x2, and x3. A matrix A would be the coefficient matrix, so negative 3. Second entry will be 0, right?
Yeah.
Because there's no x2. And then the third entry will be negative 4. Row number 2, we should have negative 1, negative 1, negative 1. Row number 3 would be 1, 0, 1. So this is the first order. Okay, so x prime equals ax. Again, we said this is first order and homogeneous, okay, because there's no extra stuff. So first of all, we're trying to find eigenvalues of matrix A, which would be determinant of A minus lambda I. Now, because matrix A is 3 by 3, right? 3 by 3, so my identity matrix should be of size 3. So be A minus lambda I3 equals 0. Okay, so I'm going to have negative 3 minus lambda, negative 1 minus lambda, 1 minus lambda, 0, negative 4, negative 1, negative 1, 1, 0. This should equal to 0, right?
Yeah.
Okay. What's going to be the determinant of this?
Went to do cofactor expansion.
Yes, if you do the cofactor expansion, it's going to be very simple in
Yeah,
this
right.
case, right? Which column or row you can go cofactor expansion?
Column 2.
Yeah, we can go column 2. So, for those of you folks that haven't taken linear algebra, don't worry. You can still do your arrow methods. Okay, but over here, I think majority of them have already got linear algebra, so we're just gonna go do that. So we're gonna do cofactor expansion along the column 2, which we notice there are 2 zeros, so we just need to do negative 1 minus lambda. Negative 1 minus lambda, and times its cofactor, right? Cofactor. So it's going to be the remaining determinant. So you take out this row, take out this column, getting -3 minus lambda, -4, 1 minus lambda equals to 0. Is that correct?
Yeah.
So we would have -1 minus lambda, and we can do cross multiplication. So we should have -3 minus lambda times 1 minus lambda, subtract 1 times -4, which is -4, should equal 0. Okay. Keep going. I'm gonna multiply -1 both sides to negate these two negative signs. So it'd be 1 plus lambda. And inside of here, I'm gonna do foiling. Okay, here I'm gonna do foiling. So I'm gonna have -3. First of all, I'm going to get lambda squared by negative lambda times negative lambda. And then what's gonna be the linear term? How many lambdas are there? If I do the following of this piece.
3.
I should have a 3 lambda and
I thought
then
you meant how many
one
eigenvalues
yes,
were.
if you combine those two, you should have +2 lambda, right? And then the constant will be -3 times 1, which is -3. And then in addition to this +4 in the end equals 0. Good so far?
Yes.
So we end up with, let me put this aside, 1 plus lambda times lambda squared plus 2 lambda plus 1, which you know this is a perfect square. That is 1 plus lambda times 1 plus lambda squared equals 0, right? So that told us 1 plus lambda cubed equals 0. Which means our lambda would be -1. How many times it appeared?
3 times.
Yeah, so multiplicity should be 3, which means we need 3 independent eigenvectors. Okay. All right, now let's go ahead with ordinary eigenvectors. Okay. So first of all, let's see how many ordinary eigenvectors there are. Okay. So we go A minus lambda, which is -1i, times v, v0, right? You guys with me?
Yeah.
Okay.
Yes.
Yep, so let's plug -1n into this matrix. So you should come up with, let me zoom out a little bit. So we should have, come down to here. So you should have -3 minus -1, which is -2, 0, -4. Second row is -1, -1 minus -1, which is 0, -1. And thirdly, we have 1, 0, 1 minus -1, which is 2, times my eigenvector v, right? Now this is a 3 by 3 matrix, so eigenvector should have 3 components. Let's call them A, B, C. So A, B, C equals to 0 vector. Okay. Good so far?
Yes.
let's go ahead and convert this into a system of equation by doing the multiplication. And you'll see some equations repeat themselves. So we should have -2, 0, -4 times ABC. So it's -2A minus 4C equals 0, right? Secondly, we have row 2 times this column. So we have -A minus C equals 0. Last row tell us 1A plus 2C equals 0. Equation 1, 2, 3. Good?
Yes.
Based on the coefficient, do you see two of the equations are exactly the same?
Yeah, first one, third one.
1 and 3, they're the same, right? So I can just reduce equation 1 because equation 1 just repeats the information given in equation 3. Okay, so the only thing that's useful is basically equation 2 and equation 3, right? Equation 2 and equation 3, apparently you have -A and a positive A, so let's eliminate the A. I can do equation 2 plus equation 3. What does that tell us?
C is equal to 0.
So C equals 0. All right, so if C equals 0, what's A?
0.
Yeah, A is 0. But B, there's no restriction on B, right? It doesn't tell you anything about a B in the system. So B can be any real number, right? All right, so if we put these information together, we should have our eigenvector, okay, which is A, B, C. Let me separate this here. Our eigenvector V would be ABC, where A and C has to be 0. So let's put 0, 0, P and B. Good?
Yes.
Can we pull out the B?
Yes.
Yep.
Yep, so we get 0, 1, 0. So this 0, 1, 0 will be the base for the eigenspace when for the eigenvalue lambda 1, right? This is only one vector you can find. I'm going to call this to be my ordinary eigenvector V1. Okay? So we have only one ordinary eigenvector, which means P that shows up in your algorithm, P would be 1. Okay, P would be 1. So what do we need to do next?
Solve for D.
Right.
Okay, now let's go for D, which is the defect, right? So for lambda equals to -1, it is defective. Defective because it has only one ordinary eigenvector, although multiplicity is actually 3.
Dr. Wu,
Yes, Milan?
can I ask how can we have more than one ordinary vectors?
Well, sure. If A, B, C, they're related to each other, remember in linear algebra, then you can separate the A and the B's.
Okay.
Yeah,
Oh,
for
yes.
example, if you have something here as, say, B minus C, here would be C, then you can separate B and C, right?
Yeah,
Then you
I
would come up
remember.
with 2, okay? But in this case, there's only one, so there's only one ordinary eigenvector.
Okay.
Good question. But going back to our original question, this eigenvalue lambda 1 is a lambda, which is -1, is defective. Multiplicity will be 3, therefore it's defect. D is K minus P, which is 3 minus 1, it is 2, right? So its defect will be 2, meaning we need 2 generalized eigenvectors. Good so far? Okay, so next we're just going to go ahead and look for these 2 generalized eigenvector. Okay, let's call those to be V2 and V3. So the question next will be looking for V2 and V3. V3 can be found from V2. So if you found V2, you can find V3 by doing the multiplication. So V3 would be A minus lambda I times V2. Get me out of here. So basically the question is, what is my V2, right? Because if you get a V2, then you can go ahead and find a V3. Okay. So next we're going to look for V2. Okay, so next we're going to find V2. Okay, find V2. In order to find a V2, because our D currently is 2, we got to first of all check A minus lambda I raised to the D plus 1 to see if it is 0 matrix. Okay. Let's plug in our lambda and then plug in our D. So we have A minus lambda, which is yeah, so plus I raised to the 2 plus 1, right? Because D currently is 2, so raised to the third is it equals to 0 matrix. Okay, so let's see. Our A plus I. This is basically our A plus I, right? So we're going to do this -2, -1, 1, 0, 0, 0, -4, -1, 2 again. So let me copy this matrix here. So -2, -1, sorry, -2, -1, 1, 0, 0, 0, 4, what was the second one? -1?
2, -1, I think.
Right? Thank you.
The other way around, I think.
No, that's correct.
Correct, sorry.
Let's see. -2, 0, oh, my bad. -4. -4. And then -1, 0, -1. Right? -1, 0, -1, 1, 0, 2. So this is A plus I, right? So unfortunately, you have to multiply it to get it to cube. -2, 0, -4, -1, 0, -1, 1, 0, 2. And further multiply the same matrix. To see what it is. Okay. If you have a calculator, you probably can use calculator quicker for this computation, but it's okay if you want to do just manual computation.
I have the answer if you want.
Show me along, you have your MATLAB?
Yes, I do.
Yes. All right, what do you get?
First row, 0, 0, 0.
Okay, so that equals to 0, 0, 0.
Second row, 0, 1, 0, 2.
Oh, is that squared? Or
I got all zeros.
okay, I think what Milan did is square.
Wait, sorry.
Is
yeah,
it 1,
square.
0, 2?
Yeah, oh yeah,
So
it's
1,
all
0, 2,
zeros.
right? And then 0, 0, 0 and times -2,
Again.
-4, -1, 0, -1, 1, 0, 2. You end up with actually all zeros, right?
Yeah.
Okay.
That's all I got.
Great. You also used a calculator, right?
Mm-hmm.
Okay, so the answer is yes. Right. So that's a good sign. Okay, if this is yes, that means, okay, so that means A minus this lambda I cube, this is a zero matrix, which means A minus lambda I cube times any V2 will still be zero vector, right? Good?
I have a question.
Yes, Martin.
When we would calculate V3, we would take to the fourth power that, correct?
Not really. You don't have to in that case. So once you got V2, which is the very first generalized eigenvector, the rest of the eigenvector will just be computed by multiplication.
Okay.
Okay. So I'll just need to get V3 as A minus lambda I times V2. You don't have to do this checking again.
Okay.
And it should be zero, because if you raise that to the fourth power, would that still be zero vector, a zero matrix?
That was my question.
Yeah, it will still be zero, right? Okay. I mean, the matrix will still be zero. So the quick way you V3 would just be V2 times that matrix. All right, so we have A minus lambda I cubed times V2 would be zero, and here, which means indicating V2 is an eigenvector of lambda, right? So here, typically, we do our V2 be A minus lambda I times V1. Let's first try this. If this will give you a non-zero vector, then you've already got your V2. Okay, so let's start with A minus lambda I. So the same matrix, you're going to use it again. Okay, same matrix, which is -2, 0, -4. And then -1, 0, -1, 1, 0, 2. And times our V1. You guys recall what's V1?
0, 1, 0.
0, 1, 0.
0, 1, 0. Okay, let's plug in to see if would that give us some non-zero matrix. So what do we have? 0, 0, 0. Unfortunately, you get 0, 0, 0 here. Right?
1, right?
Yeah, so the question here is our V2, which is eigenvector, needs to be non-zero vector, right? Non-zero vector. And currently all of these entries are 0. Okay, so that is not acceptable. Not okay. So let's revise it, right? Revise V2 to be a non-zero vector. And V2 needs to be, don't forget that V2, okay. Let me see here. V2 is independent, linearly independent of V1, right? So let's choose one of the entries to be non-zero. And remember, your V1 is 0, 1, 0, so you cannot pick the second entry to be 1. But it's okay if you want to pick the first one or last one. Okay, either one would be fine. So I'm going to say in the easy case will just be, let me fix the first entry to be non-zero. So 1, 0, 0. Is that good?
Yes.
Okay. And even though you have changed its entry, right? Even though you have changed its entry, but this equation still holds because this part is a zero matrix. Make sense? So this V2 would be the first. Okay, so this will be the first generalized eigenvector. Okay. All right, once we got to V2, then we can get to V3, kind of like chain reaction. So V3 will just be A minus lambda I times V2. So we're going to do the same matrix again. -2, 0, -4, -1, 0, -1, 1, 0, 2, and times the v2 that we just generated, which is a non-zero vector. So 1, 0, 0. Okay, what do we have here? What do you guys get? V3.
-2, -1, 1.
-2, -1, and a 1, right? All right, so that's your V3. Okay, oh, did I run out of space? I'm writing too big. Great, so here. So we have 3 eigenvectors listed. Okay. V1 is 0, 1, 0. V2 is 1, 0, 0. And a V3 is -2, -1, 1. Okay. If you have already taken linear algebra, you can tell that these are 3 linearly independent eigenvectors. We also talk about checking if these are, I mean, even if you haven't taken linear algebra, you know how to check whether they're linearly independent or not, right? You can do Ross-scans as well. Okay. So 3 eigenvectors has been generated. That's great. And next, we should start to look for the solutions. Okay. So over next, we should go ahead and find x1, x2, and x3. Okay, let me see if I have space here. Okay. So x1 would be v1 e raised to lambda t, right? So v1 is 0, 1, 0, e raised to the negative t. So that's simple. Good. You guys okay?
Yes.
All right, and then do here. Let's go for x2. So x2 is v2 plus v1t because of the multiplicity, and an e raised to lambda t, right? So v2 is what we had as 1, 0, 0. That's the first generalized. And v1 is 0, 1, 0 times t e raised to the negative t. So let's see, we can just say this is, let's just add the open parentheses here. I can add these 2 vectors together, and what I would have would be a common vector still, right? First entry will be 1 plus 0, so 1. Second entry will be 0 plus t, which is t. Third entry will be 0 plus 0, so 0, e raised to negative t. So that's your x2. Good so far?
Yes.
Okay, now let's go x of 3. X of 3. What do we here? And x of 3 would be v3, start with v3, and then v2 times t, and then v1 t squared over 2, and e raised to the lambda t. Okay. Our v3 is the generalized. So I have -2, -1, 1. v2 is 1, 0, 0. t. v1 is 0, 1, 0. T squared over 2. E raised to the negative t. Guys, am I blocking your view?
I can see everything.
Okay.
That's even better.
Is this better? Yeah. So let's go ahead and just combine the 3 column vectors together. So we should have, move down a little bit. So I should have a column vector e raised to negative t, right? First entry this time would be negative 2 plus t. Second entry would be negative 1 plus t squared over 2. Third entry will just be 1. Right, that's my x of 3. Okay, so we have got x1 here, x2 here, and x of 3 here. If you guys take a look at these 3 vectors, are they linearly independent? Let me circle these out. So this is first x1, second, and third. Are they linearly independent?
Yes.
Right? Yeah, they have 0 in the different places. And v3 is definitely independent from x1, x2 because it doesn't have 0 at all. So linearly independent. Therefore, we can go ahead and try to write down our general solution. Okay. So therefore, our general solution x of t will just be a linear combination of the 3. So c1 x1 plus c2 x2 plus c3 x of 3. That'll be c1 times 0, 1, 0 e to the negative t, negative t, plus c2 times 1t0 e to the negative t, plus c3 times negative 2 plus t, negative 1 plus t squared over 2, 1 e to the negative t. You can add them together, okay? Of course, you can leave the e to the negative t to the outside. Let me see. So I'm going to say this is e to the negative t. And let's just add the first component all together, because e to the negative t could be factored out, right? So I'm getting 0 plus c2 plus c3 times this. Second entry will be c1 plus c2t plus c3 times negative 1 plus t squared over 2. And last entry will just be 0 plus 0 plus c3. Okay, so this is your unknown vector x of t. And don't forget, this x of t contains 3 specific unknown. One is x1, one is x2, one is x of 3. So if you want to just put this in very detail, you can say my x1, one of the first unknown, x1 of t will just be e to the negative t times c2 minus 2c3 plus tc3, right? If I distribute the c3 here and I multiply e to the negative t. Is that good, guys?
Yes.
Okay. And the second unknown x2 of t would just be e to the negative t times c1. Okay, let's see what's the constant term. c1 minus c3. Linear term will be plus c2t. Quadratic term will be c3 over 2t squared. That's going to be x2 of t. x3 of t would be the last entry, which was relatively simple. So e to the negative t times c3. So that's how we get the solutions, okay? And of course, note here, to determine C1, C2, and C3, what do we need?
Initial condition.
Yes, we need 3 initial conditions, right? So if you are given with initial conditions, you can keep going and look for the C2, C3, and a C1. All right. Let me quickly guide you over what we did in this long question. Yeah, it is pretty long, right? It took lots of space. Okay. So we're going to see what we did, that we follow the algorithm. Okay. That we started from, oh, I should not go this big. So we started with finding the coefficient matrix A and find its eigenvalue. In this case, we find eigenvalue will be -1 with multiplicity 3. So we understand you need 3 linearly independent eigenvectors. And then we try to go ahead and look for the ordinary eigenvector by using our ordinary method, right? A minus lambda I times V equals 0, and you solve for the V. In this situation, we figure out V would be A, B, C, could be written as 0, B, 0. If I take out the B, I get 0, 1, 0. So first ordinary eigenvector, well, the only ordinary eigenvector, V1 could just be the 0, 1, 0. So that means our P, which is the number of ordinary eigenvector, would be 1. So guys, if you want to look at the algorithm, right? In the algorithm, it says P. So let me see here. Let me put a quick note.
Oh, no.
So P is the number of ordinary eigenvectors. Okay. So don't be confused about what is this P, right? P is the number of ordinary eigenvectors. Okay, go back to where we left. So we know there's only one ordinary eigenvector, which means defect is 2. So we need to have 2 generalized eigenvectors. We name them to be V2 and V3. Okay. The key thing is to find V2. Once you find V2, you can find V3, okay, based on the algorithm. So if we revisit the algorithm, it says we should start with A minus lambda I raised to the D plus 1 to check if that equals to 0 matrix. So we plug our D in and plug our lambda in. So our lambda is -1, D is 2. If we plug in, we should be checking if A plus lambda I cubed equals 0. Our answer is yes, good. So A minus lambda I to the third will be 0. Then that means I can generate my V2. V2 would be A minus lambda I times V1. Again, this time we've got a bunch of zeros, which is not okay to be an eigenvector, because eigenvector has to be non-zero vector. But since A minus lambda I cubed is already a 0 matrix, it times any vector will still be 0 vector, right? So as long as V2 is non-zero, V2 would be fine. So I picked a V2 to be 1, 0, 0. This will still be linearly independent from V1, and it would be an eigenvector of lambda based on the definition here. Okay. So we got a v2 as 1, 0, 0, and then we can get v3, which is a minus lambda I times v2. That's -2, -1, 1. So 3 eigenvectors has been generated, okay, including one ordinary. This is one ordinary, and these two are generalized. These two are generalized. And once you have them, you can go ahead and look for x1, x2, x3, which is 3 independent solutions to the system. x1 is v1 e to the lambda t, x2 is v2 plus v1t times e to the lambda t, and x3 is generated in that way. Once you finish those 3, then we go to the final stage of looking for the general solution by doing linear combination of x1, x2, x3. So this is just some algebra work, right? You just put them in algebra work and you get 3 entries. Those 3 entries represent your 3 unknowns. Okay, is that clear? Any questions, guys?
I would
Yes, Martin?
I would have a general question about the final.
Oh, sure. Go ahead.
So in the last final, it said that we're able to use class notes and stuff.
Correct.
Does that mean we will still be able in our final to use your presentations and YouTube videos?
Yeah, of course. You can use my YouTube video, you can use the notes, you can use whatever you have.
But you have to subscribe and like.
Oh, well, that's not one of the requirements. Any other questions? No other problems? Okay, no other questions? Great. Okay, so I think this will be the last lecture. I know some of you guys are graduating this semester, right?
Correct.
Milan, you're one of them?
I am.
Okay, anybody else who's graduating this semester?
I am not moved.
Eric, you are?
No.
Yeah, I'm like, you are not. Who else is graduating?
Jason, I think.
Yeah, I think
Yeah.
Oh, yeah,
Yeah,
Chase.
Chase.
Yeah, Chase, absolutely. Is Chase here?
I don't know.
Oh, yeah, he is here, but looks like he's not paying attention. Chase.
I'm graduating.
He doesn't have a microphone.
Oh, correct. Yeah, so he probably types anyway. For those of you guys that I can't see you at the commencement, well, they're postponing commencement, right?
Maybe. They don't know what they're doing yet.
Yeah, because
They actually sent out an